In this lecture, we introduce Markov chains, a general class of random processes with many applications dealing with the evolution of dynamical systems. As opposed to the Bernoulli and Poisson processes, which are memoryless, in the sense that the future does not depend on the past, Markov chains are more elaborate, as they allow some dependencies between different times. However, these dependencies are of simple and restricted nature, captured by the so-called Markov property. Conditional on the current state of a Markov chain, its future and past evolutions are independent. As mentioned in the unit overview, we will only consider discrete time Markov chains that evolve within finite state spaces. This allows us to concentrate on the main concepts without having to deal with some required technical details needed to study general Markov processes under continuous time and general, possibly uncountable state spaces. We will first introduce the basic concepts using the simple example of a checkout counter at a supermarket, an example of a simple queuing system. We will then abstract from the example and give some general definitions, including the central notions of states, transition probabilities, Markov property, and transition probability graphs. Afterwards, we will look at various questions, such as predicting what would happen in n steps in the future given the current state of our system. We will define n-step transition probabilities exactly and show how to calculate them efficiently. We will also discuss what could happen when we let a Markov chain run for a very long time. We will end this lecture by introducing the notions of recurrent and transient states and their importance in studying Markov chains in the long run.
In this lecture, we introduce Markov chains, a general class of random processes with many applications dealing with the evolution of dynamical systems. They have been used in physics, chemistry, information sciences, queuing theory, internet applications, statistics, finance, games, music, genetics, baseball, history, you name it. So what makes these processes so powerful and practical? Well, as opposed to the Bernoulli and Poisson processes, which are memoryless in the sense that the future does not depend on the past, Markov chains are more elaborate as they allow the representation of situations where the future depends on the past and to some extent could be predicted from the past. More precisely, we are going to consider moles where the influence of the past on the future is summarized by the notion of a state, which evolves over time according to some probability distribution. That's the link between the past and the future. We will restrict ourselves to discrete time Markov chains, in which the state changes at certain discrete time steps. The state at time t plus 1, which is here, is a function of the state at time t, and there is some noise or randomness. As an overview, this is what we will cover in this lecture. We will first introduce the basic concepts using the example of a checkout counter at the supermarket. We will then abstract from the example and give some general definitions. Afterwards, we will look at various questions, such as predicting what could happen in the future given the current state of our systems. We will end this lecture by giving some key structural properties of Markov processes. So let us start. With our example. Suppose that you go to a supermarket and start observing customers arriving and leaving from a given checkout counter. Assume that there are 2 customers in the queue when you arrive. For simplicity, assume also that customers come one at a time, that there is a single queue, and that the customer in front of the queue is the one getting served by the clerk. So what events of interest could happen then? A new customer could join the queue. This is an arrival. Or the customer currently being served is done and leaves. Departure. Or both events could happen. Now, for making our model more precise, we need to specify the processes of the customer arrivals and departures. And for that, let's use some simple discrete time stochastic processes which we have introduced before. So as usual, we first divide time into discrete time steps, say in seconds. Here, n equals 0 would correspond to the time when you arrived. For arrivals, let's assume that customers arrive according to a Bernoulli process with parameter p. And at that time steps here, there is an arrival, perhaps this customer here, and at 6 there is another customer. So during each time interval, independently of what happened in the past, with priority p a new customer arrives, and with priority 1 minus p no one comes. It may be useful to think about the following imaginary experiment. Imagine that during each time interval, nature independently flips a biased coin which has a priority p of resulting in heads and 1 minus p in tails. And whenever heads is the result, then a new customer joins the queue. So in our example here you obtain tails, heads, tails, 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 heads, tails, etc. From the lecture on Bernoulli process, remember that this implies that the time duration, that means the number of time steps between two consecutive arrivals, follows a geometric random variable with parameter p. So here in our example, that time duration of 4 is the result of a geometric random variable with parameter p. So again, once in the queue, customers wait their turn until they start being served by the clerk. And typically, when a customer starts the checkout, the number of time steps it takes to go through the entire process will depend on many factors, such as the total number of items selected, the speed or the mood of the clerk, and so on and so forth. We will model this variation by assuming that the service duration of any customer is the outcome of a random variable. In particular, we will assume that the number of time steps it takes for any customer to check out is a geometric random variable with a constant parameter q. That is, the same q for each customer. So you might have a departure here. That's correspond to that customer here. And another departure at time step 6 correspond to that customer. It may be useful again to think about another imaginary experiment to represent this service duration. Imagine the following. At the time a customer in the queue becomes the one to be served, that customer starts flipping a bias coin, which has a priority q of resulting in heads. And it does so independently during each successive time steps until heads appear for the first time, which then indicates that the checkout service is done and that the customer can leave. So here in our example, you arrive at that time here, and this customer was being served. And during that time step, that customer flips a coin, resulting in tails, 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 heads. That customer now leaves. The next customer starts being served. At that time, flips a coin, tails, heads. Then that customer leaves again. Finally, we will also assume that the processes modeling these arrivals and departures are independent of each other. Now let us go back to our made-up experiment and assume that you have arrived at 6:45 p.m. Consider the following question. What is the probability that you observe a customer leaving the checkout counter during the first time step? In our example, since there were at least one customer in the queue, that probability is then simply q. However, if that queue had been empty when you arrive, then that probability would have been 0. Another question. Will the queue be empty at 6:50 p.m.? That means 5 minutes later. Well, it's hard to tell. If the initial length of the queue had been huge when you arrive at 6:45 p.m., then the probability that it will be empty 5 minutes later will be very small. Much smaller than the probability in that case with 2 customers initially, or in that case with an initial empty queue. From these questions and answers, it looks like knowing the number of customers in the queue at any point in time not only provides a good description of the system at that time, but it does seem to capture the critical information we need in order to answer questions about the future evolution of the system. So let us define the state of our system as the number of customers in the queue at each time step n and see what we can do. So here, in our example, initially we had 2 customers. Then, time step 1, still 2 customers. Time steps 2, we have 1 arrival. So we have 3 customers. Time step 3, still 3. 4, 3 minus 1, we have a departure, equals 2. So 5 will still be 2. Time step 6, we have an arrival and a departure. So we have 2, and so on and so forth. Assume now that there is limited space in the supermarket and that no more than 10 customers can be in the queue at any point in time. We can then give a graphical representation of all possible states for our system as follows. Our system can be in 11 different states, from an empty queue with no customer to a system at full capacity with 10 customers. Let us now describe some possible transitions between these states from one step to the next. Suppose first that the system is in state 2 and that 1 new customer arrives and no one leaves. So you will transition from 2 to 3. And this is what happened in this example from time step 1 to time step 2. Suppose now that you are in state 3 and that a customer leaves and no one arrives. Then we would transition to state 2, like what happened between time step 3 and 4 here. What else? Well, you could also be in a given state at one time step and stay in the same state at the next step. How? It can happen in 2 ways. If there are no arrivals and no departure in the next step, and that was what happened between time step 4 to 5 here, from 4 to 5. Or there is 1 arrival and 1 departure, like what happened between time step 5 and 6. A graphical representation of all possible one-step transitions can be done with the help of arcs, such as here. In order to complete our model, we need to indicate the probabilities associated with this transition. So again, assume that you are currently in state 2 with 2 customers in the queue. The probability of next going to state 3 here with 1 more customer in the queue is simply the probability of having 1 arrival and no departure. On the other hand, the probability of being here and going in transition next here correspond to 1 departure and no arrival. Finally, the system can stay in state 2 like that when there is 1 arrival and 1 departure, or no arrivals and no departures. These transition probabilities would be similar if the current state were 1, 3, 9. For the 2 extreme states, the transition probabilities are a bit different. If you are in state 0, the queue is empty and you can go to state 1 with 1 additional customer with the probability P, or there is no new customer coming and you stay in state 0. And if the queue is at maximum capacity, either you stay at maximum capacity if there is no service, or you go down to 9 customers in the queue if you have a departure. So one important fact, when you are in a given state, for example state 2, and you look at all possible transition, could go to 3, could go to 1, could remain in 2. If you sum all the probabilities, P times 1 minus Q plus Q times 1 minus P plus this total probability here, PQ plus 1 minus P times 1 minus Q, you will get a total probability of 1. Similarly, if you look at this probability here, they sum to 1. And these probabilities sum to 1. It simply says that from one time step to the next, if you consider all possible transition probabilities, they all have to sum to 1. So in conclusion, this so-called transition probability graph, which is this representation here, provides a complete representation of a discrete time, finite state, Markov chain model of our simple supermarket checkout example. Let us now abstract from our previous example and provide a general definition of what a discrete time, finite state Markov chain is. First, central in the description of a Markov process is the concept of a state, which describes the current situation of a system we are interested in. For example, in the case of the checkout counter example, the number of customers in the queue provided the right level of information needed to define a useful state. Time is assumed to be discrete, that is, divided in discrete time steps. The system starts at time 0 in an initial state, and at each successive time steps, the system goes from its current state to a next one, chosen with some randomness. As a result, after n such transitions, the state of the system will be random, and so we can think of it as a random variable. Let's xn this random variable. That is, xn represents the state in which the system is after n transitions from an initial state in which it started to operate. As a shortcut, we may often say that xn is the state of the system at time n. We suppose that there is a finite number of possible states for the system to be in. Here, we have drawn a portion of a finite state space with m possible states labeled 1 to m, using I and j as generic labels. Of course, we could think of systems with an infinite number of states, either discrete or continuous, but this is a bit more complicated, and so in this course we restrict ourselves to a finite state space. Note that the initial state could itself be fixed or chosen randomly. Assume now that the system started in state 3. What will happen next? The system will evolve according to one of the possible transitions out of state 3. For example, one of these arcs. Note here that we don't have an arc from 3 to 4. As a convention, we only include arcs for transitions that can happen. Remember the checkout counter example. Because of our assumptions that no more than one person can join the queue at any time, we didn't have arcs of the type going from 1 to 3 or from 2 to 10. Also, because of the customers being served one at a time, departures were limited to one person at a time, and so no arcs of the type going from 2 to 0 or from 9 to 2. So the next transition out of 3 can be thought of a random jump, where from state 3 the system will jump to either state 1, state 2, state j, or jump onto itself. These will be the only possibilities. We want to describe the statistics of these jumps, and we will use conditional probabilities. given that at time 0 the system is in state 3, what is the probability that it will be in state j next? These will be called transition probabilities. For example, the probability of going from 3 to 1 will be P31, here P32, here P33, and here P3J. Note that these are the only possibilities. As a result, you have P31 plus P32 plus P33 plus P3J will be 1. Assume that the system continued to evolve, and after various different steps, come back in 3 at time n. Again, what will happen next? Well, this property here says that the probability of going from state 3 to 1 is again P31, the same as before. In other words, here we will say that the chain is time homogeneous. That is, these transition probabilities will be the same irrespective of the time. So this is true for all n. And the summation that we have written here for this special case is of course general. What we have is that the probability of I to j, if you sum all of these probabilities for all possible j's, you will have 1. Now, in order for this probabilistic specification to make sense and be coherent, we need to make a big assumption about the evolution of the state of the system. This assumption, the so-called Markov property, given in words here and in mathematical statement here, is in fact the defining nature of what a Markov process is. In words, what it says is that every time the system finds itself in state 3, the transition probability of going to state 1 will always be P31 no matter how the system evolved in the past up to being in state 3. In other words, no matter what path the system has followed up to the current state, the next state transition probability will be the same independent of that past. Mathematically, conditionally on knowing your current state, having more information about the past state variables does not change the transition probability to your next state. So in other words, the probability distribution of the next state xn plus 1 depends on the past only through the value of the present state xn. So you can see that as a definition of the transition probability, and that property, that equality from here to here being the Markov property. For this property to hold in any modeling application, you need to choose your state carefully. You want to ensure that the information contained in the description of your state captures all the relevant information to make prediction about the future evolution. Now, given a system, how to properly define the state variables which will allow us to model its evolution as a Markov process is somewhat of an art, and there are no cookbook recipes to do it. However, with a little bit of experience and practice, one quickly gets the required intuition to do this properly. You will be able to do so in that class. So now that we have defined what a Markov chain is, what can we do with it? Well, we usually build models in order to predict some phenomenon of interest. In the case of a Markov chain, there is randomness, and so it is natural to think about making probabilistic predictions. For example, going back again to our checkout counter example, you have arrived at 6:45 p.m. There are 2 customers in the queue, and you want to predict the number of customers in the queue at 7 p.m. Assuming time steps are in seconds, that corresponds to 900 time steps later. There is no way to know exactly where the system will be, but you may be able to give probabilistic prediction. That is, to give the probability for the system to be in a given state 900 time steps later. Our main purpose will be to calculate such probabilities, and notation will be useful here. Suppose that the Markov chain of interest starts in a given state I and that it runs for n transitions. Let us introduce the notation Rijn to represent the n-step transition probability of ending in state j. This is the initial state I, and this is the definition Rij of n. First, note that these are probabilities. Given that you started in I, after n steps, you will end up in some states with probability 1. So, the summation of all Rij of n for all possible states j will be 1. And this is true for all I, all initial state I, and for any time step n. Also, because we have a time invariant Markov chain, Rijn is also given by this formula here for any possible value of s. Going from here to here, plus s, plus s. In other words, if currently you are in state I at time steps s, and you're interested in knowing what is the probability of being in state j at time n plus s, which means n steps later, you will still have the same expression, Rijn. So, how to calculate Rijn? For some particular n, this is easy. For example, for Rij of 0, that means that there are no transition, it will be either 1 if I equal j, and 0 otherwise. In one step, in other words, when n equals 1, Rij of 1 will be the probability transition given by the Markov chain, and that is true for all I and all j. Now let us calculate Rijn for n greater than or equal to 2. We are going to apply the total probability theorem and break up the calculation of that quantity by considering the different ways that the event of interest can happen. Again, the event of interest is to go from I, state I, to state j in n time steps. There are many ways for that event to happen. Let's group these many different ways as follows. Let us consider the first n-1 steps and group together all possible ways of going from I to a state k, a given state k, in n-1 steps. And this wiggle path here represents all possible ways of doing that. Using the definition above, that probability of going from I to k in n-1 steps will be R I k of n-1. Now, assuming that you ended up in state k in n-1 transitions, the probability that you end up in state j in the next transition is simply the one-step transition probability, pkj. So, altogether, the probability of going from state I to state j in n steps and in being in state k after n-1 steps is simply Rik n-1 times pkj. Note that state k can be any of the finite number of possible states of our system. In summary, all such paths can be represented by the following diagram. So again, from time 0 you're in state I, and you want to be at time n in state j, and you break down all the possible ways by first looking at what would happen after step n-1. You can be in state 1, state k, all the way to state m. We have calculated these expressions here. This is what we have done here. This is for state 1 and state m. So the overall probability of reaching node J is obtained by an application of the total probability theorem. It gives the following formula. So this is corresponding to the total probability theorem. Here, this is the calculation that we have done here, and we sum over all possibilities for k. Where did we use the Markov property in this calculation? Well, the key step here was when we said that this probability here was pkj. Going back to the calculation that we had here, this was in fact the probability of being in state j at times n, given you started in state I and you were in state n-1 in k. And that probability being equals to the probability of xn equals j given the last time, that is due to the Markov. And this is pkj. This is the recursion in the following sense. Assume that you have calculated Rik n-1 for all possible values of I and all possible value of k. And you had stored all these values, m square of them. For any pair ij, you can now calculate Rijn using that formula, and you can do it in essentially m multiplication and m-1 additions. That is, in a number of steps or number of elementary steps proportional to m. You do this for all m square pair of ij at the time step n, and then you repeat for n plus 1, etc. So this is the essence of the recursion. Here is a variation, that is another recursion, for computing Rij of n. You start at I, and suppose that in a one-time step you find yourself in state k. The probability here is the one-step transition pik. And then, given that you are in state k, what is the probability that you will end up in state j in n-1 step? Will be, again, looking at this formula that we had here, Rkj of n-1. Again, you have to consider all possible values for k here, and the application of the total probability theorem gives the following alternative recursion. Rij of n, the sum for all k equals 1 to m of pik times Rkj of n-1. These two recursions, this one and this one, are different. They are both valid and could be useful depending on the specific questions you may want to answer. Finally, note that if initial state is itself random, that is given by a random distribution, this is the initial distribution on the state, then the state probability distribution after n steps will be given by this formula. This is the state after n step is simply that. And this is yet again an application of the total probability theorem. Let us now illustrate with an example the calculations of n-step transition probabilities that we have just discussed. In this example, we are given a two-state Markov chain, and as part of the input, the one-step transition probabilities between these two states. So, given that you are in state 1, the probability that you will next go to state 2 is 0.5, and the probability that you will stay in state 1 is 0.5. And given that you are in state 2, the probability that you will next go to state 1 is 0.2, and the probability that you will stay in state 2 is 0.8. Now, suppose that you start in state 1, and you would like to calculate the probability of being in state 1 after n transitions, or after n steps. With our notation here, this is R11 of n. That probability can happen in two ways. After n minus 1 steps, you end up in state 1, and then for the last transition, you stay in state 1, or after the first n minus 1 transition, you end up in state 2, and then you transition back to state 1. Assuming that you start again in state 1, and you would like to calculate the probability that you end up in state 2 after n steps, you could apply the same logic. But these are probabilities. And given that you started in state 1, after n steps you will either be in state 1 or in state 2. So R12 of n is simply 1 minus R11 of n. And this system of two recursions is enough to propagate R11 of n and R12 of n as a function of n. Let us do it and fill the blanks here. As indicated before, the case for n equals 0 or n equals 1 are simple and do not require the use of the recursions here. So, for example, for n equals 0, R11 of 0 will simply be 1, and so as a result R12 of 0 will be 0. And again, R22 of 0 will be 1, and as a result R21 of 0 will be 0. For n equals 1, these are the simple one-step transition probabilities. So you have 0.5 here, and 0.5 here, and R21 here are 0.2 and 0.8. The next cases for n equals 2 becomes more interesting. So to reach n equals 2, R11 of 2, two options again. You can go this way with the probability 0.5, or you can go from that to here with the probability 0.2. So here we obtain a total probability of 0.25, here probability of 0.10, and when you sum these two probabilities, you obtain 0.35, which is R11 of 2, and as a result you get 0.65 for R12 of 2. Then you can follow the same process for n equals 3, n equals 4, etc., etc. I will not do it here, but this would be an interesting exercise for you to do the next several steps, perhaps within an Excel spreadsheet. But suppose that I tell you the number for n equals 100. And I tell you that the number that you obtain here is about 2/7. So as a result, the numbers that you are going to have here is about 5/7. Let us then apply the simple recursions in order to find the values here for n equals 101. R11 of 101 will be 2/7 times 0.5 plus 5/7 times 0.2 will be 1/7 for the first one plus 1/7 for the second one, and so we obtain again 2/7. And if you do the same calculation, you will end up with 5/7 here. This is an interesting fact. When the system starts in state 1, the probability that I found myself in state 1 after a long period of time seems to converge to a constant value, in that case to the constant value of 2/7. Assume now that you want to do the same calculation for R21 and R22. In other words, you start in state 2 and you're interested in knowing the evolution of these R21 of n and R22 of n as a function of n. Again, I will let you do it, but I can tell you that these probabilities will also seem to converge to a constant, and in fact will converge to something that is exactly the same, 2/7 here and 5/7 here. This is a second interesting fact. Irrespective of where we started, either from state 1 or from state 2, the probability of being in a state 1 after a long period of time seems to converge to the same constant, 2/7. So in some sense, for that particular example, the importance of the initial state vanishes as time goes by and does not influence long-term probabilities of being in any of the two states. Note that this is not true at the beginning, starting at state 2. The picture after few transitions will look different than if you had started from state 1. So the initial state does tell you something at the beginning, but this vanishes as time goes by. We describe these convergence properties by saying that the Markov chain eventually enters a steady state. What does this really mean? Does it mean that the state of the Markov chain itself becomes steady and eventually stops at a given place? No, the state of the system will keep jumping forever. What becomes steady are the probabilities that describe Xn. After the Markov chain enters steady state, then at any time, if you take a photo of the system and ask, what is the probability that the chain will be in state 1 on that picture? It will be 2/7. By the way, the steady state of being in state 2 is greater than the steady state of being in state 1. Does it make sense? Yes, state 2 is a little bit more sticky than state 1 in the following sense. When you get to state 2, the probability that you remain in state 2, which is 0.8, is greater than the corresponding probability for state 1, which is 0.5. So to conclude, this Markov chain has exhibited some nice long-term properties. Is this always the case for any Markov chains? Let us see. We have observed in the simple example from the previous clip that when the Markov chain initially starts in state 1, the probability that it finds itself in state 1 after a long period of time converges to a constant value, in our case 2/7. In addition, if the Markov chain initially starts in state 2, the probability that it finds itself in state 1 after a long period of time also converges to the same constant value, 2/7. Are these two properties of long-term convergence and of vanishing effect of the initial state over the long-term convergence always true? Mathematically, we are asking the question, is Rij of n when n goes to infinity? The answer is that for nice Markov chains, this will be true. But this is not always true. Consider the first question. Does Rij(n) always converge to something and n goes to infinity? Look at the following simple Markov chain. When in state 2, you will never be in state 2 at the next transition. You will end up next in either state 1 or state 3. However, no matter where you end up, you are sure that the next transition will bring you back to state 2, either here or from here. In other words, for n odd, R22 of n will always be 0. And for n even, R22 of n will always be 1. And so R22 of n will never converge. It will always alternate between 1 or 0. Convergence has failed. That chain has a periodic structure, and we will see in the next lecture that if periodicity is absent from a chain, then we don't have a problem with convergence. Consider now the second question dealing with the vanishing importance of initial states when convergence occurs. For this, consider the following Markov chain. If you start in state 1, there is no way you can escape. You are certain to stay there forever. So, R11 of n will always be 1. On the other hand, if you start in state 3, there is no way you will ever reach state 1. So, R31 of n will be 0. The initial state of where you started does matter in this example, and its influence never vanishes in the long run. The second nice property has failed here. And here this has to do with the Markov structure, where some states are not accessible from some other states. And we will address this in the final portion of this lecture. Finally, let us calculate R21 of n for large N. So you start in state 2 and you ask yourself, what is the probability that I will end up in state 1 after n steps for n large? Well, when you start in 2, you may stay in 2 for a while by doing this kind of transition and this transition. But eventually, with probability 1, you will escape. Either you will go to state 1 or you will escape to state 3. And in that case, you will never go back to 2. If you're in 1, you will never go back here in 2, and from 3 you will never go back to 2. Because of the symmetry between these probabilities here, 0.3 on this side and 0.3 on this side, when you do escape state 2, you are equally likely to escape toward 1 or toward 3. So what you have is that R21 of n will be 1 over 2. In the last example of the previous clip, we have observed that the initial state of where the Markov chain starts can matter, and that in some cases the influence of the initial state never vanishes in the long run. So when we wanted to calculate the probability of ending up in state 1, knowing that you started in state 1 gave you that probability, and if you started in state 3 you had another long-term probability, and in case you were started in state 2, then you were equally likely to end up in being in state 1 or in state 3. We have said that this was due to the fact that some states are not accessible from some other states. Our goal here is to make such a statement more precise and formal. In order to do so, we will classify the states of a Markov chain in a transition diagram into two types, recurrent and transient. A state is said to be recurrent if starting from that state, no matter where you go, there is always a path to come back. A state is said to be transient if it is not recurrent. It means that starting from that state, there is at least one place where you can go, and then there will be no path back to it. For example, starting from state 8, no matter where you go, there is always a path back to 8. So 8 will be said to be a recurrent state. For the same reason, 7 will also be a recurrent state, as well as 6. Now, what about 5? From 5, the only state where you can go to is 5 itself. So 5 is also a recurrent state. Let us look now at a state like state 4. From 4, there is the possibility of a path going through 2, then 1, and then going to 5, from which there is no path back to 4. So 4 cannot be a recurrent state. It is then called a transient state. For the same reason, starting from 3, there is the possibility that after doing many transitions around here, eventually you will end up being in either 2 and then go to 6, or you will eventually be in 1 and then go to 5. And from 5 or from 6, there will be no path back to 3. So 3 is also a transient state. And it is clear that for the same reason, 1 will be a transient state and 2 will also be a transient state. Now, if a state is transient, like 3, 4, or 1 or 2, it means that it will be visited only a finite number of times. And in the long run, the probability of being in a transient state will converge to 0. The recurrent states of a Markov chain can be grouped in different classes. Here, in this example, we have two such classes. Here, this is one class, and here, you have another class. What is so special about these classes? Well, within one class, like for example in this class, all recurrent states have a way to communicate between each other. But there is no communication between recurrent states of different classes. From that recurrent state here, you have no communication with that recurrent state here. No communication in the sense that there is no path joining that state to that state or that state to that state. The existence of more than one class of recurrent states, like in this example, in a Markov chain, will be the telling sign that initial states will matter in that chain. It's pretty clear here that if your Markov chain starts in state 5, you will never end up in state 6, 7, or 8. And if you start in one of the states 6, 7, 8, you will never end up in state 5. So depending on where you started, the long range probability of being eventually in state 6 will not be the same.